Okay. Now I could have given you a little better diagram, but this will work. We're asking sketch free body diagram showing all the forces. Well, let's see. There's a tension force here. And there's a tension force here.
Ideally, we're trying to get this third stage.
Now, these two tension forces are not equal in magnitude. I mean, they might be if you have just the right masses and coefficient of friction and all that stuff. We'll call this T1, we'll call this T2. Fair enough? Okay, well, then we have the weight. And let's call this mass M1. So this is M1G1. And it's a vector. And let's say this is M2G2. And we'll say this one is and I'm not sure why I'm putting subscripts on the G because I just having so much fun putting subscripts and things I couldn't stop myself. Okay. So anyhow, that's on M1G, M2G, and M3G. And you could designate those any way you want. I didn't ask you necessarily to put arrows on or to put labels on them, but I'm going to put labels on them because we're going to do a little something with it. Okay. Okay, any other forces? Okay, so people say, well, you got a normal force and so forth. Yeah. Okay, well, let's think about why you have more forces than you do, because that's really, you don't want to, I mean, you will get to where you do these out of habit, but if you get something really unfamiliar, then don't put it past me to ask something really unfamiliar. Or just for something unfamiliar to just naturally come up. All right. As it is now, unless T2 is really big, this thing is going to be accelerating somewhere in this direction. And it's not going to stay on that ramp. It's this force and this force. I guess if these forces balance out just right, if this was a pretty big force, and this had an even bigger force with enough upward component, they could potentially balance to keep this thing on the beam, on the ramp. And, one person's pulling here, another person's pulling here. You could adjust it so that the tension, the net tension in those two strings or whatever is sufficient to keep this thing on the surface of the ramp. Okay, but that's not likely. We don't have anybody out there. We just have tension forces, unless it'd be possible for these masses to balance in such a way as to make that happen, but it's not likely. Okay, so the basic idea is, let's assume this thing's going to stay on the incline. And the way the forces are drawn right now, it isn't going to stay on the incline. Okay, so as soon as you see that, you say, oh, well, what's holding it up? Well, there's a normal force in this incline. These two tension forces could combine to either pull it down into the incline a little bit or pull it up off the incline a little bit. Okay. But probably not that much. So we have the normal force. So we have, I'll just call it vector F sub n. All right. So that makes it a little better here. Okay. Now, what other forces do there have to be? Okay, so if you look at either of these falling weights, the only force either one of them has is acceleration of gravity. As the weight, you know, the mass times acceleration of gravity. And each of these is just going to accelerate downward of 9.8 meters per second squared. Okay. And what prevents that is an upward tension in each of these rows. Now, the upward tension in this row, implicitly, these are frictionless pulleys. So I didn't write that down. And if you really wanted to include friction in the pulleys, you could have. But I wasn't expecting it and I wouldn't regard it as necessary. Later, it might be, but right now, okay, so this tension, if the pulley is frictionless, is just equal and opposite to this. The two ends of the rope are being pulled on. I mean, one of them's over a pulley, but the pulley's not exerting any tension, exerting any force in the direction of motion of the rope. Okay. So the two tensions are equal and opposite. Two ends are trying to pull together with equal tensions. Okay. And similarly down here, and I didn't leave myself a lot of room to draw this tension vector, but I'll draw. Now it's, since I put arrows over these, you know, I better just take the arrows off because of course, this arrow is not parallel to this arrow. So this vector would not be equal to this vector, right? And the way I've got it labeled right now, I've got vectors being equal. So I can put I and J components on any of these if I know the angle. If I know the angle of this incline. Okay, so we got some tensions. Okay, anything else? Okay, now most people seem to have forgotten this, or at least at first glance, I didn't look at that closely. But mu is not equal to 0, so there's a frictional force. So there's a force of friction here. And we don't really know if it's in this direction or that direction. If this is a really big weight, we could be pulling this thing up the incline, in which case friction would be down the incline. Friction is going to resist motion. Make sense? Friction is always in the direction opposite. And we put a little question mark on this. Just to remind ourselves that we got to work some other stuff out before we know what direction friction's in. Okay, so we got to look at the effect of all these other forces before we know whether the net force is going to be down or up the incline. And then we add friction, and friction might be big enough to hold the thing static. So if the system is at rest, it'll stay at rest. It might be too big. I mean, the net force, even if the friction is equal to the maximum, which is mu sub s times the normal force, right? Even if it's the maximum, it can be, your net force might not be 0, so the thing might be moving, in which case you have to go to kinetic friction. Okay, so I'd be a little more,
because of that, we now have access.
give you a little more information. That's static friction, it's not equal to 0. Of course, if any friction is not equal to zero, static friction isn't zero. You gotta be careful about static and kinetic friction, okay?
That's false.
Now, that's free body diagrams. You start with that diagram, then you set up your equilibrium equations, at least the Y forces are in equilibrium. The X forces, you have to work it out. And the other thing that many of you did, and it's a good thing, and everybody should have. There's an X-axis. Here's a Y-axis, right? And my perpendicular is really bad. You got a bad perspective on the board, and I wasn't that careful. But you might really choose to project the weight vector here.
There's no way I'll always operate. You do something like that.
And yet,
they can do whatever the heck they want because they're starting all that off because it's
M1 times the Y component of G and M1 times the X component of G. When you do free body diagrams, make sure they're complete. Make sure you then know how to write your equation. I'll write some stuff down. I could write your Y forces are in equilibrium. So what do you have in the Y direction? You got normal force, M1GX. If we have an angle theta, we would then probably say that that force is in the negative Y direction. Normal force is in the positive Y direction. And then we would have T1 X component. And that's what? Well, in the X direction, theta is in this direction, so it's angle theta below the X-axis. It's going to be the cosine because that's the adjacent side. You just have to know those angles. So it's going to be negative T1 cosine theta. And then you're going to have T2X, which is positive T1. Oh, wait a minute. I've been doing a lot of this sport. I got enough sleep last night, so I got no excuse. We're doing the Y components. Y components are going to be the sine.
Protein. And our body breaks it down into.
Except that this was going to be the cosine. Okay, if here's theta, this side is the adjacent side. So I was right when I wrote cosine. Then I started to write cosine on these, and I realized that they're perpendicular to a different line than this. They're reference to the horizontal, whereas this angle's with reference to the vertical. So I wasn't careful enough when I did that, but there we have it. Does that make sense? Yeah, if you just draw little triangles here, X direction, Y direction, identify where theta is, you can immediately see whether you're using a sine or a cosine. Okay, well, those are the only forces acting on the block.
So just researching those and trying to see if theory was that if you kind of revert that rather than protein rich.
So that sum of the Y forces for the block on the incline are 0.
That was his theory. It's interesting.
Now you can write out the X forces, but until you know what the tensions are, you can't do much with that. You can also look at the entire system. And that's only part of the solution. That's a key part if you're analyzing it piece by piece. Okay. For the entire system, what's the net force? Well, if counterclockwise is the positive direction, then the net force is M2G minus M3G, and then it's plus the frictional force.
All right. Build a protein that's like proteins low.
And then it's minus M1G cosine theta. Now, does that make sense? Well, I'll just say that we're not including the normal force because it's balanced by the Y component of the weight. So these two forces can kind of be regarded, when you look at the system as a whole, as a system of 3 weights chained together, with part of the system sliding over this incline.
So I changed it just before class and mine take a little while.
Those two forces are sort of internal, but they're sort of 2 external forces. I would say they're external forces, but they're in balance. Okay? This tension and this tension and this tension and this tension are all internal to the system. Okay? They're all part of the chain. They're all acting as part of the chain. There are better ways to say that, but intuitively we'll say it this way.
So, yeah.
And they are equal and opposite. Each one of them is equal and opposite to the other. But they're internal forces that are equal and opposite. You can regard these as external forces that are equal and opposite. Okay. Again, you regard this whole system of 3 weights and the ropes as one object. And then you can see that T1, the 2 T1s here and the 2 T2s here are internal to that system. Okay. And they're not having any effect on the acceleration of the system. Well, we have this. There's your net force. We know this, we know this, we know this. Now we'd have to calculate, yeah. We'd have to calculate this as mu s or mu times or less or equal to mu s times your normal force. Okay. So we can then say that this is
is always better on the local scale. Maximizing what you were.
And I did it again. I wrote cosine theta here. That's the sine of theta. That's this. So that M1 GX, look for the right color. And your M1 GY is negative M1 G cosine theta. Okay, you put all that together. The cosine and the sine are just going to give you numbers. The M1G and the mu s. All this is, if all this is known, then you have an expression for F net. Now, the only problem is F net is actually less than or equal to this because the force of friction is less than or equal to mu s times M1G cosine theta. Okay. Now I'm going to erase that less than or equal and make it equal, but I'm going to put a condition on it.
Because it's our duty as sort of workers to figure out what are the levels of each of these that are particular plan.
I'm going to replace mu s by mu k.
Whatever.
If you're moving down the incline. Because if you're moving down the incline, then you do have a frictional force that's equal to the coefficient of kinetic friction times the normal force. And down the incline is the negative direction if counterclockwise is taken as positive, which it generally is if you have something that's got some rotational aspect to it. Now you can decide that the force or that the positive direction is when the thing is sliding down the incline, if you prefer. That would be counterclockwise. That's all right. Some of the signs would change. You can think through that. You still get the same solution. Okay. If you know it's moving up the incline, then the sign here would change. The friction would be in the opposite direction. And of course, if you know it's moving up the incline, then you're going to draw your friction as if it's in the opposite direction. If you don't know whether it's static or not, okay, then you figure all these forces out and figure if the static friction is enough to keep them balanced. In other words, if you know it's stationary, start with the assumption it's static, but test it, make sure that the static friction that you get is sufficient to balance all the rest of the forces. Okay, well, we're going to start talking, we've been talking about energy for a while, but that's what we really want to go into today. Actually, I keep worrying about this camera blurring, so I try to get something on the board before I move, but this camera doesn't blur unless I change the focus. Okay, let's say you got this situation. You got some force acting on an object that has a displacement from here to here. And let's just say, for simplicity, that the object is moving in a straight line, and there's your displacement. Okay? You could, for example, have an object sliding up an incline with this force, a nearly vertical force, but of course, it makes less than a right angle with the direction of motion. You can understand that if this force is big enough, it'll pull that object up the incline, right? Okay. You can resolve that force into two components.
What else?
F parallel and F perpendicular. Now, if this object did happen to be on an incline, then F perpendicular would be in the direction of the normal force. So the normal force would probably be less because the way you're pulling here, you're helping keep it up off of the incline. Okay. So this doesn't affect the velocity.
Fluctuation for radiation. That actually goes. So.
If whatever object the force is acting on is constrained to move on a straight line. That would be the case if it was on an incline and if this component of the force was not greater than the weight of the object in that direction, okay?
However,
If this force isn't big enough to pull it up off the plane, then the strength of the plane constrains it from moving downward relative to the plane. This force isn't enough to pull it upward, then we would say the object is constrained to move along a straight line. And there are other situations. That's just one you can grasp because that's what we've been talking about.
Question 6, what is the most efficient roller?
It might be that this is a bead moving along a frictionless wire with a lot of tension so it doesn't bend, okay? Plenty of other cases. You might be pulling a wheelbarrow up a incline. Okay. In this case,
Video of this form, they found when they switched strips, they were no longer recording their neighbor. Therefore, they're not that and they're eating all the time rather than.
I'll say that this work has magnitude F parallel delta S. Because this thing isn't doing any work on it. In other words, I've said many times that this force is totally equivalent to these two components. So that this force can be eliminated and you only have this one and this one. This force moves in the direction of motion. This force doesn't move anything. It doesn't do any work. It doesn't affect the motion, and if it doesn't affect the motion, it can't affect the kinetic energy. It might affect the frictional force that's resisting it up along that ramp, but that's indirectly. It does not directly affect the motion of the object.
representing the fruit section.
More completely,
Because of that.
work is a dot product of F and delta S.
Which those planets don't have chilling hours.
Which by definition,
Apples, for instance, have a chilling hour,
is F delta S times cosine theta. It's your definition of dot product.
vegetative.
Actually, definitions like A1, B1 plus A2, B2, the component definition, but it's equivalent to this in a fairly simple manner. If you just use the law of cosines, the two are seen to be
So anyway.
equivalent, synonymous. Okay.
Go up and down. The other one that was incorrect is I just.
So the work is F cosine theta delta S.
Put 60 all down. But that's what it said in the lecture, right?
Now, why don't we just say F parallel delta S? Well, if you're careful about whether F parallels in the direction of delta S or not, you can kind of get away with this, but you really want to be able to use the dot product. It's a little more sophisticated, it's a little more accurate, it's a little more reliable.
Average load is slow, which affects.
And of course, F parallel here, I said that magnitude is F parallel delta S. Here I say it's F cosine theta delta S. Well, F parallel is F cosine theta. Now we want to consider if your force was back this way, then F parallel, the component of F along the line of S, okay, it's still, here's your angle theta. So if you multiply this by delta S, you're going to get a negative because theta is greater than 90 degrees. It has a negative cosine. Now, let me give you a big picture here because people are fuzzy with this picture. Here's your definition of sine and cosine. Here we've got a unit circle, meaning a circle of radius 1. Your polar axis is here. Here's theta. Then you got your X and Y axes. You've got a triangle here, and this leg is the cosine of theta. And this leg is the sine of theta. You should always have that picture in your head. You should draw it every time you use it, so you reinforce it. You need it for the rest of your life.
Usually people say, oh, I thought I after Mother's Day. There's lots of there's ways around it. Our neighbor.
And you can see that if you're over 90 degrees, between 90 and 180 degrees, which this angle is, the cosine is definitely negative. This thing is definitely going to be in the direction opposite this direction. And the product is going to be negative.
That black plastic. So if
theta is less than 90 degrees, the work is positive.
also consider that, sort of the value added, the battery takes when you're almost takes on value added. I like that.
So what's that tell you? It tells you if this thing is being displaced up the incline, then this force is going to tend to increase its kinetic energy. It's going to tend to speed the object up. Now, depending what other forces might be there, because I didn't say this was the net force, this is a force you're using to pull it. Okay? And that's the work you're doing. Friction might be doing work against you. You might be losing speed, while still doing as much work as you would to speed the thing up if there was no friction. In this case, you're doing negative work. You're pulling back on the object. Okay? And you pretty much do that just by hanging on the object and changing your angle of impact and hoping you got enough friction between your boots and your incline to exert this much force. Okay? Without causing you to let go because your grip isn't strong enough, or pulling your arms off just in case you're chained onto it. Whatever. Okay? You're slowing the object down. You're doing negative work on it. And you might not be slowing it down. It might be just dragging you along. It might be 280-pound Mastiff. Okay, and I've been around a 280-pound Mastiff. I know if there was a leash around that thing's neck and it decided to go that way, it would. There's nothing I could do about it. Very friendly dog, just big old goofy, lethal, 280-pound lethal. He happens to sit on you. Okay, so just as an example. All right, make sure you understand this. Make sure you have an intuitive understanding of it. Now, if this is the net force, then work by the net force equals F dot delta S, which equals change in kinetic energy. Because the change in kinetic energy is always the work done by the net force. I don't know if I can get this example into the space I've got here or not, but I'll try. Okay, mass M, F net greater than 0. Your acceleration's F net over M. Okay. You don't have to assume accelerations F net's greater than 0. It could be less than 0. It works out just as well, except we're going to start from rest. And assume a displacement delta S, which it could also be delta X. Well, VF squared equals V naught squared plus 2A delta S, right? Okay, I'm going to let you do this so you can be proud of yourself. A can be replaced by F net over M. So rewrite this familiar equation, substituting F net over M for the acceleration.
It's also, it can also be food, it can also be environmental.
See what you get.
The categories are somewhat super. See, it's of those patterns.
Okay, so our example is mass M, F net. We assume it's greater than zero, but it doesn't matter. Except that we're going to assume initial velocity equals zero. Well, your acceleration's net force over mass. That's Newton's second law. It's locked in stone. Displacement is delta S. So we write the fourth equation, VF squared equals V naught squared plus 2A delta S. Substitute F net over M for the acceleration and solve for F net delta S. Well, here we do it. Here's the equation. Instead of A, we write F net over M. Multiply the equation by M over 2, and that'll isolate F net delta S here. If you do that, you get M over 2 times VF squared equals M over 2 times V naught squared plus F net delta S. Now, if you already let V naught equals 0, and I said you could, then you got F net delta S equals MVF squared over 2. That's just your kinetic energy, isn't it? If you left V naught in there, and if you made it V naught equals 0, okay, but then you're going to understand this, then what you have here is the final kinetic energy minus the initial kinetic energy, right? Which is a change in kinetic energy. And that's your basic work energy theorem. And it can be extended to vectors. Could be F net dot delta S. Your acceleration would still be, if you're constrained to the path delta S, straight line path, you would have it. Now, you do a little calculus, and you could say that instead of multiplying F net over M by delta S, you would integrate F net over M times delta S. Okay. And that'd be a little bit more involved. But some of you use some pretty good calculus in homework, so you're gonna need to continue to do that. We'll talk about that a little more when I've seen all your homework. Yeah. Okay. So, let's get that done so I can talk a little bit more about any deficiencies or problems or things you just need to see that we haven't talked about. Okay. There's the whole theoretical underpinning of the whole chapter 7. If we have coiled spring attached to something solid, and we're pushing on it, then the way the force acts actually, I'm going to talk about the force extending the spring, which is equal and opposite to the force compressing an ideal spring, just like talk about a positive force. Okay. So this is a stretch. No, it is. This is the force. This is the stretch.
You have one party interest, and there are readers working on three more party centers. But right now, may have seen it. It's a different, it's called the Hardy Orange on series. It's also called a triangle.
For an ideal spring,
You're heavily so does yours industry have?
I'm going to break this into two forces.
Yeah.
The applied force is equal and opposite to the force exerted by the spring. Just like if I've got that 300-pound mastiff trying to hold it back, I'm fine as long as my force is equal and opposite to his. Okay, but the harder he pulls, the more force I've got to pull with. Well, the more force I pull with, the more force he pulls with. That's not a really great analogy, but it popped into my head and I thought I'd use it. You understand if you're pulling that spring back, if the spring's pulling in the opposite direction. Okay. So this is the applied force. This is the force of the spring. For an ideal spring, as long as you're in the ideal range, the force exerted by the spring is a linear function of your stretch. And your stretch is just measured from the equilibrium position of the spring. You know, spring's relaxed and you start pulling on it. So the force exerted by the spring is negative kx. Among other things, that means if I extend the spring out past its equilibrium position and then release it, it's going to take whatever's attached to it, pull it back that way in the opposite direction of its displacement. It's displaced this way, it'll accelerate the thing back that way. With a decreasing force, because as the spring gets closer to its equilibrium position, it exerts less and less force. That makes sense? Okay, so let's say we stretch the spring from 0 out to x equals capital A, which when we study simple harmonic motion will be an amplitude. So I'll need capital A right here. Okay. There are two ways to answer this. Since we have a straight line, we can see what the average force is, right? So the average force will be halfway between the initial force and the final force. Now here, this line, this horizontal line that's all mixed up with this equation here is F equals K times A, because the function is applied force equals Kx. Here X equals A, here F equals Ka. That should be totally obvious. Ponder that until it is, if it isn't, because that's just fundamentally what the graph is telling us. The average of F out, which is F out bar, is then half that because this is a straight line. It starts at 0.
It gets really, there's actually two, maybe three different associated. So first, look at our pitch. Put it in. It's the
And then that's 1/2 Ka, that's your average force. And your delta X is just from 0 to A, so delta X is A, right?
They are.
So let's be sure we understand that.
What's our temperate version of that? Yeah, potatoes, right? So they're our temperate problems. The vision tomorrow is kind of the problem. And
That's 1/2 Ka squared.
So we have collocation. Also though, it's with allocation and collation. The three different actually looks like here they all know zero. And then it's got it. We're mostly growing this here or not further ahead.
Okay, so the work done by the spring is the average of F spring. Well, F spring is negative Kx.
How do we know?
This line here is
The arrow families have this combination of spat, in this case, is a piece of
F equals negative Ka.
spatula shaped flower. The spade is the
Force by the springs negative 1/2 Ka. So this is negative 1/2 Ka
also
times A equals negative 1/2 Ka squared.
a lot of the house plants are in there. They're
Alternatively,
Monstera, what are we talking about with it?
this is the work by the applied force. This is the work done by the spring. They're equal and opposite because they're exerting equal and opposite forces through the same displacement. More generally, if you don't have a linear function for the spring, you've got to do an integral. Either way, the work is represented by the area under the curve.
Could we add zero to our list? Or do you want to call it gold zero?
So the shaded region in both cases is the work by the spring. You know that's identical to the integral of this function from this point to this point. So by calculus, the work done by the applied force is the integral from 0 to A of
What added there? But
Kx with respect to X.
and coefficient is, let's see what the. Anybody in here find some information out about this controversy?
And there you have that. Now you can read what else your book says. If we wanted to integrate from 0 to X, we'd have 1/2 Kx squared, right?
It is, and they're not edible. So it's something you really don't get mixed up.
Now, I've already told you that potential energy is equal and opposite to the work done by conservative force. Conservative force being a path-independent force. Now, you're not responsible for that right now, but I just want to keep repeating this because people never end up using it when they need it. It comes in the next chapter, but we've already talked about potential energy. Equal and opposite to the work done by the conservative force. The conservative force is the force of the spring, not the force I apply. That's not conservative. Okay, if I apply the force here, I do work. Okay, it takes work out of me, but I can't get that work back by pushing something backward goes. Okay, my force is non-conservative. The spring, on the other hand, if you ignore the fact that it heats up a little bit and loses energy to the environment, an ideal spring doesn't do that. And a really good spring doesn't do much of it. An ideal spring exerts the same force at this position, whether I'm pulling back or relaxing back to the equilibrium position. Unlike friction, for example, when you're moving in that direction, friction acts in this direction. When you're moving in this direction, friction changes its direction, so it's not path independent. You want to start getting used to that idea because I found it a tough idea to get used to. I assume you will, because I see that most of my students do. Okay. Okay. In any case, then this would be the potential energy of the spring when you have it out at its extension A. If you're at extension X, well, then you'd replace A by X, it'd be 1/2 kx squared. Anyhow, be sure you understand this about the spring. Your book talks about it, and it's involved in some problems that are going to be due. And your book gives a nice exposition of that. So you're gonna, okay, I kind of paused. Be sure to read what your book says about springs and so forth. You can read it pretty quickly if you understand this. You're going to recognize most of it. Now, there's a fairly involved derivation of the work energy theorem. Compared to the derivation I just did, it's fairly involved. Where in the world is the one I just did? That must be on the other side of this board. Okay, now your book derives the same thing for a non-constant force, or just a general force, where your F net delta S is the integral of F net with respect to X between two limits. And they prove that comes out to the same thing, 1/2 MBF squared minus 1/2 MB naught squared. Okay? You're not going to need that proof to do the problems. And we can talk about that proof a little bit next time so you understand at least what the context is. Officially, this course only requires first semester calculus, which doesn't get that far into integration, but it does get far enough into integration that we can talk about simple integrals and the meaning of an integral. And that should be helpful to you because it'll help continue to develop your understanding of what integrals are and what they tell you. Yes. It doesn't use anything over first semester calculus, but in a way that most people don't really understand very well, having had first semester calculus. I didn't. I had a really good calculus course. And so have you. But I hadn't actually had the course. I was taking the course as I was learning the physics. So trying to learn physics and calculus together was an interesting exercise. Okay. You all ought to be in better shape to understand it than I was, but it's still not trivial by any means.